this talk will not be about like explaining what the actor model is, but I think even if you're not familiar with the actor model, then it will probably give you some insights and hopefully motivate you to investigate what it is. So who is familiar what the actor model is? About half the people. Who tried Akka on JVM or Akka.NET or Microsoft Orleans? Yeah, few hands. Who is a big fan of OOP, object-oriented programming? Yeah, more people than people who tried Akka. So yeah, there will be some OOP rant, I must say, but my GitHub nickname is Object, which actually says something about my passion, in the past at least, for OOP, for doing object-oriented programming. So there are some sort of mindset changes for me, which the actor model brought. And I will try to explain it to you and maybe to encourage you to try it. So my name is Vagif. I'm consultant at a Norwegian company, Miles. Last years I've been working mostly with F# and functional programming, but what I'm going to present, it has nothing to do with functional programming or like C# or Java. So it's mostly about the model itself. So no matter what language you choose, you can use the actor model. So you can ask questions. I will try to answer them in the end. Also, you can reach me outside if you don't have time. Please come to me after the talk or find me on Twitter or email. And so our product. I'm working in a small group doing development for Norwegian Broadcasting Corporation. It's a Norwegian analog of BBC. So what we do, we make it available for the public media files. It can be TV programs, radio programs, news clips. I mean, everything which today is multimedia. So this is our product. It's called Media Distribution Engine. So our architecture at large is we get some commands. They're coming through some queues. It can be, we use very much RabbitMQ, which actually also internally implemented using the actor model in Erlang. But for some queues, it's Azure Service Bus. It doesn't matter actually what queuing system you use. Then we enrich our data with some MediaSet metadata, and then we fetch files from media archives and we send them so they will become available from content delivery networks, CDNs. And of course, thinking about that this is Norwegian analog of BBC, it's a quite hard requirements for scalability, for availability. So it's a really mission critical system. So of course, failure may happen, but that's also one of the reasons why we chose actor model. With actor, you have resilience. So when actor goes wrong, there is a chance to retry something. So actors are supervised. So our architecture at large is what's like in the center. It's an Akka cluster. We have command adapters. We get messages from durable queues. We process these messages. We transform them into commands to file managers, and then we go to command dispatcher, and then later stage is transfer protocol, which uploads files to so-called origins, which then send them to content delivery networks. So why did we choose Akka and the actor model? The most important reason that we believe that the actor model is, it gives you a chance to proper model the real world processes and interactions. And I think that's the most important lesson which we have learned. I will try to focus on it. It has very simple threading model. Basically, you don't need to care about threads. If you search in our code base, you will not find a single instance of word thread or lock. And anyone who is working or who was working with concurrency problems, with thread sharing, understand that it's actually a big advantage if you can abstract your model from threading issues, because I mean multi-threading is hard. It's really hard to get it right. So actors are great as finite state machines. So each actor has its own state machine and just gets messages sequentially, processes them. Actors are reactive, so they are very cheap to create. An actor, an empty actor, it just takes a few hundreds of bytes. And then while it's not processing message, it's just sleeping. It's reactive software. So you can use this laptop, which I'm using now for presentation, to run an actor system that will have millions of actors. For example, for the whole Norway, with about 5 million population, you can actually process a lot for the whole population on a small machine, as long as there are limited sort of number of concurrent messages. Of course, if you have billions of messages, if it's online trading system, then of course you need great hardware. But since actor system is reactive, then you don't really need to pre-allocate threads, to pre-allocate memory for them. So you can just allocate them as you go, and the actor model framework takes care of it. And of course, there is resilience, which I already mentioned, that if something happens, if exception happens, then the supervisor, the parent actor, can intervene and do decision for you what to do. So it actually helps to have cleaner code. You don't need to have this try-catch a lot in a lot of different places. Again, unfortunately, I can't say very much more about this, because there is another talk or maybe another course about the actor model. Here, it's mostly about lessons. Why Akka cluster? Of course, you can use the actor model in a single process, on a single machine, but of course, for any like serious or large system, you need to run it in the cluster, both for scalability, also for to implement failover. So you have redundant system, you have durable system, and in case your node goes down, then the system automatically will rebalance your nodes and will continue operating. Also, actors, they have referential transparency. So the actor itself doesn't know that it's running in a cluster. It's also a very good advantage. So you don't really program individual actor as, okay, I'm a member of the cluster. So the very important lesson, the most important lesson, which I probably will be using like more time than I will use on some other lessons. Don't use OP to model interactions. And it took time for me to really understand it, because I came to the actor model with my OP background, and then I started programming actors, thinking about them as like managers, dispatchers, in a sense, like we do using them in OP. And I think that was wrong, and that really gave me heavier model, less readable code, and actually less reliable system. So Alan Kay, who invented the term, who coined the term OP, said that he never had C++ in mind. So this is an irony about, like, behind OP term, that when we think OP, what comes to our minds is that, okay, OP, this is C++, this is C#, this is Java. But in fact, it was not. When OP was thought through by creator of the term, Alan Kay. And what Alan Kay was saying about objects actually is essential for the actor model. So he was thinking about objects as biological cells and individual computers on a network, only able to communicate with messages. This is exactly what actors do. Also, the actor model, it's quite popular now, but the original principles were formulated back around 1973. And they based them very much on real-world modeling. So they were trying to follow, to model, make it easy to model physical processes. So OP to Alan Kay, it meant only messaging. So, and again, this is exactly what actors do. You don't call method on an actor. You just send a message, and actor itself decides what it does with this message. So, when I was learning OP, and then I like probably most of you who went through OP path in university, or when we were reading about OP ourselves, about languages like C++. My first OP language was C++. And then at that time, I didn't really think what was wrong with such representation of the dog. Okay, we have a dog which inherits from mammals. Oh, it's great, it's inheritance, which I no longer value as much as I did when I was learning OP. But the most essential part of OP is that you combine the data with operations on them. You have operation bark, and then you have a dog. You create an object of dog, and then you call my dog .bark, and then you pass you want to bark in English language, for example. And then now when I read this code, and then actually ask myself, I mean, why was I so impressed with it? Why didn't I understand that there is something wrong with that? So immediately when you enter multiple threading, when you enter parallel processing, then there are some questions which are hard to answer. Okay, so you created a dog, and then you ask it bark, and then somebody in a different thread get pointed to that dog, and then calls at the same time bark method and ask to bark on a different language, or maybe to ask to stop barking. So what will happen? And then in many cases, such objects, they will crash, or they will corrupt data. And this is why when we talk about classes in C#, C++, and Java, in documentation, often it says whether this class is thread safe or not. And you have in .NET, you have dictionary, which is not thread safe. You have concurrent dictionary, which is which can handle concurrency. So if you think about dog as a real object, then actually what OP gives us is a dead dog, basically, or puppet dog, because you know, dogs are not waiting for us to tell them to bark. Who has a dog? Who has dogs? Yeah, I have a dog, and I can tell you that no way I can control barking of my dog. I can just send a message to my dog, bark or not bark, but it's his own justice. How? Mostly people just ignore my messages. Yeah. So what OP actually models is these puppets that are controlled from outside without telling us anything, how this outside control is implemented. And this is why especially this enterprise level software written in Java and C# is full of managers and dispatchers, because even though there is a bark method implemented on the object of the class of the dog, dogs are not entitled to decide when they're about to bark. It's a dog manager which can call this method. So immediately we make this complicated. I would say overcomplicated, because wouldn't it be closer to the real world if you have a dog represented by an actor which receives a message, which can be please bark, and decides what to do with that message. So this is exactly what was thought about OP by Alan Kay many years ago, and this is exactly what the actor model does. So, so that's a sort of first important lesson that took actually quite some time for me to grasp and to start changing my code, which I thought I knew how the actor model works, but it still took time before I I got this code right. And so please, even if you don't do the actor model, question the roles of managers and dispatchers in your system. So, and especially if you started doing the actor model. So every resource is a candidate for being an actor. And typical mistake, and it was my mistake at least, when you start using the actor model, then we try to put actors to so-called aggregate roots. Okay, customer is an actor, user an actor, shopping cart probably an actor, but we deny actors for things like files, for example. Well, file is not an actor. Probably we need some file manager, which is an actor, which will manage some files. And actually, anything which has some physical representation is a good candidate for actor, and I will try to explain it actually on files. Like how we can eliminate a file dispatcher. So this is was part which we went through in our project. So we upload files. So every file, of course, needs to be managed by same worker, same thread, you can say. So if we have file ABC and we're uploading to the origin, then if there is a retry, if there is a new version of the file, if we want this to go through the same worker, it's like managing bank account. Like you don't want concurrently do updates to the same bank account. You want some sort of responsible for this entity. So in the first version of our system, we had file dispatcher, which and we use consistent hashing to bring files to file processors. Okay, by evaluating hash based on file name or file path, we can bring it to the worker which is responsible for that file. And then so we have actors, and they have the routing strategies, and consistent hashing one of them. Some others is round robin, broadcast, random, tail, and so on. So consistent hashing. And we thought that no, we can't work without consistent hashing, because this is how we ensure that the file is processed by that specific worker. So there is no conflict. The same file is not processed by multiple actors. So how this can be eliminated? Well, just assign an actor to a file. And those who are familiar with languages like Erlang, you know that this is how by nature works in Erlang. So and it solves all your problems. You don't need to think about consistent hash. Okay, I have a file. Okay, I will create an actor which is responsible for that file. So all operations on that file will be sent to that actor. And actors are single-threaded, so there is no concurrency problem. Everything goes sequentially. You have this message ordering. So, so you immediately simplify this architecture. So that's important. Maybe it looks like this detail is not very important, but as a mindset, it's important to change your mindset. Anything, any resource is a potential actor. That brings us to maybe the second most important lesson that we have learned is keep actor persistence at aggregate root level, unless you need it. You really need it at a lower scope. So this brings us to DDD, who is familiar with domain-driven design. yeah, almost everyone. And with VTD, you have this aggregate roots. You have also value objects, and then in the beginning, we design how we implement persistence of our actors, because actor can persist its state. So when actor is awakened with a message, actor can load its state. Okay, I'm in this state, and that's quite important for some actors. So we have media set controllers. Media set is a TV program, for example, or radio program, and then it consists of files. And we have some workers which upload these files to origins or CDNs. And the first generation persistence had persistence like almost everywhere. We have media set events on, like you have this TV program events, then you have file events, and it also persisted. And also these CDN events, like from that origin, from Akka, we get event that file was uploaded from Microsoft, we get that there was a failure, and so on. So it was persistence everywhere. It was very efficient on each actor level, but it was really hard to get it the state of the aggregate truth, because in the end we need to know whether the TV program or radio program that we are dealing with is uploaded. Is it ready to be streamed? So we needed to get these events from individual actors, get its states, and it's really slow to get its state, and it brings unnecessary complexity. So second generation persistence, that all events, all persistent events, they are accumulated on media set level. Media set, again, it's a TV or radio program, anything that can be streamed. So you can have a lot of child actors, worker actors who doing their job. But it's, first of all, it's always easier to deal with when they're stateless. And if they are stateful, what we do when they are created, they get their state from the parent, from media set, and then continue working. And then when they state change, they send back events to parent who persists them. So that made our event journal and the whole persistent layer much more simple. So this is our second generation persistent events flow. So only media set controller writes to event journal. And event journal, it's who's familiar with event sourcing, that this is basically implementation of event sourcing. So each actor lives building its state from events that have been persistent through its lifetime. So lesson 3, don't expose actor's state directly from the persistence layer. That was another mistake we did. So actors, they live in cluster and then have its state, which they get from event journal. And then, of course, we often need to query the state, not just for operational reasons, but also for like reporting reasons. We have some dashboards. So in third generation persistent, everything went through Akka cluster. So there is some dashboard which wants to show the state of upload of a TV program. Okay, it goes to Akka cluster, give me the state of this TV program. Okay, we have a cluster, we have multiple nodes. Find this actor, request its state, and of course with actors you don't have methods on actors. You can only send messages. So you're just sending message get state, and then it send you message back. So it was really slow, and because we simply forgot about CQRS, and that was a bit ironic because actually we all knew about and respected CQRS before we started working with Akka. But often when you start with a new tool, it's like you get the only tool is a hammer, and then then you just deal with that hammer. So okay, we have actors. Let's just get state through actors. And no, don't do that. You have separate reading and writing models. So event journals, they're mostly for actors to live. And then if you want some reporting dashboards, implement your read side, reporting side, not using your actors. You will find much more performant and easier to manage system. So then another lesson, leave active state validation to actors themselves. So that's also about how to model real-world processes and real-world objects. So when I wake up in the morning, one way to act would be that I get a telephone from somebody who tells me that what I need to do. Another way is that I probably should be able to manage sort of myself. So when I build my state in the morning, I can use, of course, some tools, maybe my phone with some reminders, but I myself should probably be responsible for finding out what I need to do today. So with the actor model, our first generation, we had the so-called media set monitor. It was also actor, which was trying to monitor which programs are not fully uploaded and just trying to send commands, okay, try again, correct error, and so on. And then if you think about a TV program actor, doesn't it know that it's not fully uploaded? I mean, it's an actor. It should be responsible for its doings and wrongdoings and should be able to fix the state. So actually, whenever this actor is alive, it knows better than everyone else. Okay, by the way, I have a TV program consisting of 10 media files, and this file was not fully uploaded. I need to retry it. Of course, it knows the best. But the little problem with that is that actors are reactive. So they don't always stay in memory. And this is what makes the actor model very efficient. So we just implemented a set of media set reminders. So please remind some actors, but don't remind what they need to do. That's a principal difference. First version, we reminded them, okay, you please wake up and fix that error which you have with some files. No, don't do that. Just remind them, wake up. Actor wakes up and then he decides, okay, by the way, my state is this and expected state is that. Actually, we operate with so-called desired and current state. So what actor does is just simply math. Let's evaluate the difference between desired state and current state. Okay, the difference is that I have two files which needs to be uploaded. Let's do that. So it's simplified code quite a lot. Lesson 5, and actually it's very close to lesson 4. Let actors schedule periodic reminders themselves until they have nothing to worry about. So actors should be self-managed. So they should know best what they need to do, and they should just schedule reminders to themselves to periodically wake up until they have nothing to do. And typically in media business, like when you have a news clip or radio program and then you collect files, and it can be quite hectic where there is a transcoding process going on and you get necessary qualities. Once you're done, that's it. This actor responsible for this TV program may not need to worry about things at all. Or maybe sometimes there can be difference in rights, broadcasting rights, so program needs to be removed and then restored. So then actor wakes up. So, but they need to be able to take care of about themselves. So, and to implement that, there is some ready code which we can use based on persistent reminders. There is a quite popular library Quartz, which have support for in Akka, and we're using a different library called Akka Persistent Reminders, which is open source library. This is actually for .NET. For on JVM, there are some other tools, but Quartz also available for Java. So the sixth lesson is tell actors what to do, don't ask them. Again, it's like every time I look at such lessons, it's always because we haven't properly modeled real-world processes. With Akka, you have two methods available for actors. Well, there are messages, but one is tell, you're just sending a message to actor, but there's also ask, where you send message to actor and then you wait until actor's response. And we no longer use them. In the beginning, we thought, oh, so convenient. I can just tell actor what to do when I don't need immediate reply. If I need immediate reply, then I just ask and then I get a reply back. That breaks the whole actor model. First of all, let's look at performance. So if you use tell on that performance benchmark is a few years old, so it was a less powerful machine than I'm having now. But basically, on that machine, it was a small laptop. I was able to send like 4 million messages a second to the actor. While using async task, it was about 500,000, and when using ask, it was about 150,000. So it was like 30 times difference, and it's a huge performance difference because internally, actually, there is a lot going on to implement this ask, because actors sort of the actor model doesn't natively support that. So what is done? There is a intermediate actor is created, which manages these messages and implement this wait, and also it breaks the whole concept of reactive software. Like suddenly you are a model, you don't do anything, you're just waiting for a message. Also, it breaks the nature of sequential messaging for actors. So actors get a message and suddenly it gets asked, which means that, okay, I need to answer that. Maybe it takes time. But what if actor gets another message? Okay, should I process that message? No, I need to answer to the ask. So it's actually the logic of ask is quite complicated. So it's very good explained in one of the several articles. I just mentioned this one. Okay, how can we deal when we really need an answer? Well, you just use the so-called aggregation pattern. So let's see, you want to find the cheapest hotel in the area, and then you want to ask 1,000 hotels and get the best price. What you do, instead of just asking every hotel, you just send 1,000, million, how many hotels in the area messages, and then you go in the state awaiting responses. So actors are FSMs, final state machines. So the actor goes to a different state. Okay, I'm in the state, I'm awaiting responses, but I'm still getting messages. I can react, I can, which means that the actor knows that he's awaiting response, but he doesn't block anything. So, and then he can receive new messages, he can receive responses from these hotels, and then he doesn't need to wait for all 1,000 or million responses. If suddenly comes a price which is very good, it can say, okay, I will stop. I will not wait for other messages. And if and those messages which can't be processed until the actor made a decision, they're stashed. So there is a stash. It's a buffer of messages that will be processed later when I go to a different state. So basically, use final state machines to and use tell. Use just one-way messages instead of using pretending that you can do two-way messaging. So seventh lesson is begin with non-cluster system. It's I think it's probably obvious that if you want to try Akka or Microsoft or Linux or whatever, Proto-Actor, whatever actor framework you will want to try first with non-cluster system, because it's a different dimension which you need to sort of explore. And actors, as I mentioned, they have nothing to do with clustering. Actor doesn't know actually that it's running in the cluster, but the way you design the system can be different. So first, try to build non-cluster system, and then you try to deal with clustering later. And it also corresponds to what Martin Fowler said about distributed object design, like don't distribute your objects. So there is a risk that you will start distributing your objects if you like start with cluster system in the beginning. So in our case, we implemented our system first as non-clustered, and then we realized that we need, of course, clustering. And then with clustering, it took several more months before we got it right using Akka cluster. So now this is a console application which shows the state of nodes. You see that most of nodes are up, and somewhere in the beginning there is a node which is weakly up, which means that the node is starting. So, and load is distributed between these nodes. Apply domain-driven design when planning cluster sharding. So once you start using the Akka model in the cluster, then you will want to take full advantage of it. So when there is a message coming to your entity, in our case it's TV program, for example, then what the Akka model framework does, it will find the node which is responsible for that message. So typically every message should have some sort of entity ID which helps to identify who is responsible. Like in bank transactions, it will be bank account. So it's very important that you have these entity IDs. It helps determine who is responsible to handle this message, and it will guarantee that there will be only one actor processing that message. And if the node goes down, the system will be rebalanced. So it's another actor will be created in a different node which will be responsible for that message, but it will only be one. And then things very easily fall in its places when you apply DDD rules. So this is how, in our case, we have this Mediaset publishing actor. So we have this cluster shard, and there's entity, it's Mediaset controller, and then it sends work to other actors which also run in the cluster, but it's not sharded actors. They're just it's worker actors. So they use another type of clustering actor, cluster pooled router. So this is cluster sharding. So you have message queue, message parser. We have to extract entity ID from that message. So in our case, it's a code of TV or radio program, and then we find this entity, and then it is sent to the shard. And then you this sharding and using of sharding regions, it's basically, if you read about how clusters are implemented, it doesn't need to be the Akka model. You can read about how database works, how RabbitMQ works. So it's the same principle. Yes, so I think we have about 10 minutes left. A couple of more lessons. Avoid cluster singletons. It's the same advice that also goes for singletons. Don't create singletons without good reasons, and the same goes for cluster singletons. Example of possible mistakes which we made. We have a health check, which is now system running as a singleton. Why we did that? Because we thought, okay, our health check, it checks the network system, it checks RabbitMQ, Azure Service Bus, MySQL, you name it. So it performs a lot of different checks. Let's just run it once. There is one actor that's responsible for all that, but then we implement it as a singleton, which means that if that node goes down, we don't have health check. Alternative is just to run this health check in every or in multiple, not necessarily in every node, but in multiple nodes. So you don't depend on one specific node. Yeah, it's a bit more expensive. Like you do the check for whether RabbitMQ is available or not from multiple nodes, but it's probably advantage of having it in multiple nodes. It gives you more safety for the system than if you run just in a single node. Also, it makes it more performant. And lesson 10: don't rush to heal split brains. Who knows what split brain is? probably half of the audience, is that if you have a cluster, then it performs certain tasks. And there can happen network partition, that parts of the cluster will act as independent systems. And the consequence can be catastrophic. Let's say you're running a bank system, you're sending out payments, and then you have a split in your clusters, and then you start running duplicate payments from two partitions of your cluster. So it's it can lead to very severe economical consequences. And so in some environments, in some systems, that you can't really afford that. If you can afford that, in our case we can, because we're just uploading files. So the worst what happen if you have split brain for a few seconds, let's say, or maybe some milliseconds, perhaps the file will be uploaded twice. So we will handle that. Because split brain resolution, basically it's about killing nodes, which we don't know what's happening to them. And then, and of course, if you don't have control with a node, so network is split, the node itself should decide, should I kill myself or should I stay alive? So often what is used is static quorum. Okay, we know that if it goes below a certain number of nodes, let's kill the whole partition. It's dangerous to run it that way. So another strategy. So eventually you can actually kill the whole cluster. Very popular strategy is keep majority. Okay, majority is always right. So if we have a split brain, those which are in minority, they will kill themselves. So we have a split, and then, okay, these guys, they kill themselves. So, and there are some other strategies. One of them is keep oldest, and the reason why it's keep oldest and not newest, because the oldest node always runs your singletons. Singletons are created at the start of the cluster, and they are, of course, created in the oldest node. So we just keep the one which has most functionality. And we keep the rest, even though we have only a couple of nodes there. So, but what happens, especially if your system is running in the same physical place, that partitions are really temporary. And then within a few seconds, they will be resolved. So consequences of your started killing nodes and then maybe restarting them, they are more serious than if you simply wait. Again, if you can afford waiting. In case of like financial applications, situation may be different. So your domain, your requirements to handling this situation with split brain will probably tell you the answer. But in majority of systems, I'd say it's better to wait without having this radical action. So currently our Akka cluster is set up with no split brain resolver. And it works more stable than when it had split brain resolver strategy. So those are 10 most important lessons from implementing the actor model in our project. And we can continue learning, and we continue sort of revising our decisions. I think that brings me to the end of my presentation.